So this video is the third of three, numbers 19 to 26 in the multiple choice, paper 1A. So 19 has an electron interacting with an atom, and a photon is emitted, and it says the electron has a speed v, and the frequency of the photon is f. Double the speed of the electron, what happens to the frequency of the photon? Well, the electron the energy is 1/2 mv squared, so v is squared. So if we have twice as fast, it's 4 times the energy of the electron, so then it would be 4 times the energy of the photon. Energy is directly proportional to frequency, so 4 times the energy of the photon means 4 times the frequency of that photon. Choice D. Okay, next. So number 20, we have, again, it's broken weird. So here's like the setup. We have the phototube, we have the ammeter, we have a voltmeter, and a variable power supply. And it says the graph shows how current varies with voltage for 3 different beams, X, Y, and Z, incident on Y, the collection plate, at different times. And so there's statements. 1, X and Y have the same frequency. 2, Y and Z have different intensity. 3, Y and Z have the same frequency, and which is correct. So let's take a look at the graph, and I can tell just from the relationship of voltage and current when the voltage at which the current is 0. So the voltage when the current is 0 would be the stopping voltage. And we know from the photoelectric effect equation, the energy of the emitted electron is HF, F frequency of the light, minus the work function. But remember that energy can be related to the voltage as QV. And then we have stopping voltage, Q, the charge of the electron, times the stopping voltage is equal to the Planck's constant times the frequency of the light. Now, point is, one of these statements says X and Y have the same frequency. If you have the same frequency, that means you have the same stopping voltage, because Q and H are constants. And so X and Y do not have the same voltage. X and Y, when the current is stopped, X and Y have different stopping voltages. So it's choice 1. Statement 1 is not true. And just by process of elimination, that means A is not right, B is not right, and D is not right. So that gives us C, 1 and 2 only. I'm sorry, 2 and 3 only. 2 says Y and Z have a different intensity. 3 says Y and Z have the same frequency. Y and Z do have the same frequency because they have the same stopping voltage. So that is true. Ding. And then Y and Z having different intensities, it probably has to do with the slope of the current versus voltage graph. I do know that intensity is related to the intensity of the light is related to the number of electrons, the rate, I should say rate of electrons. But just by process of elimination, we know statement 1 is not true, so that gives us C for our answer for 20. All right, let's move on. Now, number 21, this is more of an E1, not an E2 thing, talking about the Bohr model. And so there's a couple of things here that I don't love this question. It's specifically talking about Bohr model for hydrogen. So remember that, right? So for the Bohr model, angular momentum of electrons is quantized. That is absolutely true. I mean, it's a formula right in the data booklet. We have MVR, which is the angular momentum, is NH over 2 pi, right? So quantized in amounts of H over 2 pi. And MVR, the angular momentum, that is MVR. So yes, that is absolutely true. Are electrons described by wave functions? Yes, but is that like, does it go with the Bohr model of the hydrogen atom? No, it does not. Electrons never exist in fixed orbitals. That is true, but that's more of a Schrodinger wave model, not dealing with the Bohr model, so not true. And then electrons continuously emit radiation. I suppose that's true as they're accelerating, but that's not part of the Bohr model. So Bohr model would be A, angular momentum is quantized. So it's not like, I think all of the statements are true, but A is the one that goes with the Bohr model. But this one's maybe a little bit moot because it's E1 anyway, dealing with the Bohr model, not E2. It's still a good question. I'm gonna let it sit because I think it's the only one that is not E2 in this set, except for number, what was it, 12 or something? That was a double. Anyway, 22. So 22 says light is incident on a metal surface, electrons are released, the intensity is increased, not the frequency, but the intensity. So if you have more intensity, that is going to, the rate of emission of electrons is going to increase. More photons means more electrons. So the rate of emission goes up. So it's not B and it's not D. Oops, it's not C, my bad. But what happens to the kinetic energy? Well, the kinetic energy, E, is HF minus the work function, which has nothing to do with the intensity. And so the kinetic energy is no change, but the rate of emission goes up. And that agrees with the Bark scheme, D. All right, let's take a look at 23. 23 seems pretty straightforward, but it's actually made me realize something. So first of all, energy of a photon, it's easy. E is HF equals hc over lambda because V or C equals F lambda. So E equals hc over lambda for energy. That is easy. It is not going to be C or D. But momentum of a photon is given by the de Broglie wavelength equation. Lambda is h over p, so p is h over lambda, and so that gives us A. But I just realized that, and I'm like talking about de Broglie wavelength as if it's unique to particles, but if we have wave-particle duality, that wavelength is true of both photons and like classical particles such as electrons, because if the photon is a particle, just as the electron is a particle, but the electron acts like a wave, just as a photon acts like a wave, they are interchangeable. So that de Broglie wavelength equation applies. That equation applies to both photons and also matter particles like electrons. And yes, anyway, 23 is A. Okay, 24. Okay, so, man, the IB really loves these which statements are true kind of things. So anyway, behavior of electrons, electron emission from the photoelectric effect, electron diffraction as electron interacts with an atom, and emission of radio waves as a result of electrons oscillating in a conductor, evidence that the electron behaves as a particle. Photoelectric effect is definitely photon as, wait a second. This is electron as a particle. I'm thinking photon as a particle. Well, I can tell you this, it's definitely not 2. Electron diffraction, as an electron interacts with an atom, in order for the electron to diffract, it has to have wave properties. It's talking about particle properties, so definitely not 2. And by process of elimination, which is the way a lot of these things work, 1 and 2. No, not 2. 2 and 3. No. 1, 2, and 3. No. 1 and 3. All right. Going back to the statements, just to reiterate, again, I love how these freaking pages break. Not terrific. So, anyway, the electron emission is a result of the photoelectric effect. Yeah, that's more evidence of the photon as particle, but yes, that's an electron being emitted as a particle, so yes, 1. And then emission of radio waves is a result of electrons oscillating in a conductor. Whenever a particle, a charged particle accelerates, it emits electromagnetic radiation. So yes, it's a charged particle accelerates. So yeah, that would make sense. Definitely not 2. 2 is classic wave, like diffraction. That is a wave thing, right? So yeah, it's 1 and 3 for number 24, and that is choice B. Okay, we have 2 more questions left. 25. All right, so this question is tricky. And actually the answer is A. So for the kinetic energy, that's kind of simple. higher frequency. So a higher frequency of light means that the kinetic energy of the photoelectrons is going to increase. So not decrease. So it's either A or C. Now you might be tempted to say, well, it's the same intensity. So if it's the same intensity, it's the same number of photoelectrons per second. And so it's going to be the same number, same number of photons per second. And so it'll be the same number of photoelectrons. But we have to be careful. It's that intensity. The intensity is the power, which is the rate of the energy. So the same intensity does not necessarily mean the same number of photons. It means the same number of, say, joules per second or electron volts per second. And so with a higher frequency means it's going to be a higher energy per photon. But if the rate of energy is constant, that means there are going to be fewer high energy photons per second, because each photon has more energy, and if the energy delivery is constant, there are going to be fewer photons. Fewer photons means you're also going to have fewer electrons. So the kinetic energy of the photoelectrons increases, but the rate of ejected photoelectrons decreases. So that is A. Tricky, tricky. And now we have 26, the last question. 26 is like asked differently, but it's the exact same principle as number 25. So yeah, same principle as number 25. Increase the frequency of the photon. That'll increase the energy of the electron because it's HF minus the work function. But with a constant intensity, there are fewer photons of a higher energy so that the power is constant. But higher energy photons means there's fewer of them, and so therefore fewer electrons emitted because there are fewer photons hitting. And so the number of emitted electrons goes down, but the energy of the emitted electrons goes up. So 26 is B. And that's it. That's all of the paper 1 questions for E2. And this is the end of video 3 of 3. Thank you.